From 2016, he is serving in the present position. And as far as his academic interests are concerned, he has written a book in nonlinear dynamics entitled Dynamics of Nonlinear Time Delay Systems. And this book was published by Springer Complexity Series. And I understand that he very recently has published a review article in a famous journal, Physics Reports, which is very difficult to publish, but he has done it. And as far as his research interest in nonlinear dynamics, he is working on different topics in nonlinear dynamics. To name a few, I cite, he is working on bifurcation and stability analysis, synchronization of chaotic systems in chaotic systems, and network theory, and coupled map lattices, and time delay systems. I have pointed out only a few areas, but if you want to learn more about his work, you can visit his homepage. And with this short introduction, I invite Dr. Senthil Kumar to deliver his lecture. Senthil, over to you.
Yes. So good morning, all. So thank you, Professor Senthil Velen, for your kind introduction. Yeah. So as suggested by Professor Senthil Velen, so I'll be giving some basic introduction to nonlinear dynamics in the first part of my lecture. And specifically, I'll be focusing on, after giving introduction to linear and nonlinear systems, I'll be focusing on non-integrable systems, and eventually I'll also discuss with you about the stability analysis of a fixed point, and then I switch over to amplitude depth and oscillation depth, and specifically I'll be focusing on reviving of oscillation in coupled dynamical systems by introducing what is reviving and what is the requirement or what is necessary to revive oscillations in coupled nonlinear oscillators. And after those introduction, I'll be discussing some of our recent works along this line. Yeah, so to begin with, yeah, so almost every systems, all systems in nature keep on changing the state, right? So for example, if you look clouds, rivers, oceans, they keep changing their state, right? Similarly, animals born, grow, they die, and so on, right? Chemicals react, and so on. So this system, all physical systems, change their state continuously as a function of time. The change of state of a physical system as a function of time is called evolution, and whose steady constitutes the subject of dynamics. So then a natural question arises, how do such changes occur, right? So how do a physical system change its state? So naturally, so the change of state of a physical system occurs due to the nature of force acting on the system. For example, just think of any natural system such as pendulum, which is being acted upon by restoring force, and planetary system is being acted upon by gravitational force, moving charges by electromagnetic force, stationary charges by electrostatic force, and atomic nucleus by nuclear force, and so on. So the change of a state of a system occurs due to the force acting on the system, right? So now, yeah. So for example, let us consider the linear harmonic oscillator. And here the force is given as minus kx. And using the Newtonian formalism, one can write the equation of motion as md square x by dt square as minus kx. So now if we plot the force, the force as a function of x is just linear, right? It varies linearly. Here the force is linear, and consequently the corresponding dynamical system is also constitutes a linear dynamical system. And here is an example for a nonlinear force. Is an anharmonic oscillator where we have cubic nonlinearity here in the force, and the force is plotted here as a function of x. Here it is of course it's not a linear function, right? It's nonlinear in nature, and correspondingly its equation of motion becomes a nonlinear equation. So see, so depending upon the nature of force, whether it is linear or nonlinear acting on the systems can be classified as a linear or nonlinear dynamical systems. So what is, why do we have to give such emphasis on the nature of force acting on the system? Does it make any profound difference on the dynamical nature of the system? Yes, it is indeed, it makes a profound difference on the dynamical nature of the system depending upon whether the force is linear or non-linear. As I already said, if the force is linear, then the corresponding physical system, we call it as a linear system. If it is non-linear, we call the corresponding dynamical system as a non-linear system. And as a consequence, the set of the governing equations of a linear system can be casted as a set of linear differential equations, whereas for non-linear system, the equation of motion can be written as a non-linear differential equations. Okay, so and again, so depending upon whether the system is linear or non-linear, the properties, the dynamical properties also changes drastically, and so as the physical and mathematical properties changes. So similar drastic change will also be there in the physical and physical properties, and also the mathematical formalisms dealing with such linear or non-linear systems. For example, for linear systems, so well-known analytical tools, established analytical tools such as Fourier transformation, Laplace transformation, spectral methods, Green's functions, and so on, available. Whereas for non-linear systems, in order to analyze non-linear system, there is no well-established analytic tool in general is available for non-linear system. And as a consequence, we know our understanding about the non-linear systems are very limited, even now. Okay. Yeah. So now, if given a differential equations, after rationalization, if the degree, if the power of the dependent term x or its derivative dx by dt is either 0 or 1, then those differential equations are classified as a linear differential equations. Here, if you look at here, the power of x dependent term is just 1 here. Also, dx by dt is just 1 here, right? So such equations are classified as a linear differential equations. On the other hand, if the dependent term or its derivatives has power greater than 1, then such differential equations are classified as nonlinear differential equations. You can see here you have a cubic nonlinearity here. So this is obviously a nonlinear equation, and here you could see the derivative, right? Dx by dt has the power 2, and hence it is clearly a nonlinear differential equation. So the nonlinear differential equation can be broadly classified as integrable and non-integrable systems, and I'll be focusing only on the dynamical aspects of non-integrable systems, whereas you have experts there. Even Professor Sandil Valen himself is an experts in integrable systems. I'll be focusing on non-integrable systems in the further few slides. And before that, so let's begin with simple setups, going from LC circuits to LCR, then forced LCR circuits, and let's look at the dynamics. And before that, let's look at the elements of the circuits, LCR circuits. Okay, so we have a linear resistor here. So where if you look at this current voltage characteristic, it is completely linear, right? So whereas we have a nonlinear resistor where the current voltage characteristic is no more linear in nature. So we have linear and nonlinear elements. So also we have here a capacitor. So where again this is a linear capacitor and this is a nonlinear capacitor. If you look at the QE characteristic, again for the linear capacitor, it is linear. It's completely linear. The voltage varies linearly with respect to Q charge, right? Also here, if you look at there is a non-linear function, Q and V are so non-linear function of each other here. And similarly, we have a linear inductor and a non-linear inductor where the characteristic display the linear behavior and non-linear behavior here. So yeah, so now let's look at just simple LC circuit. These are all linear elements. These circuits are constructed with linear elements. Here's the circuits. All the circuits are linear circuits. Let's first look at the LC circuit. Then we'll just go back by introducing an our resistor, and let's look at the dynamical behaviors. Then we introduce a forcing into it, and then we look at the dynamics exhibited by this linear circuit with external forcing. So then we will move on to the nonlinear circuit. Let's move on. Yeah. So for this figure, where this is just LC circuit, right? So by applying Kirchhoff voltage law and current law across here and voltage law across the capacitor, you can write this equation. So then taking the derivative of this, right? So then you can just plug in for DI by DIL by DT over here, so that you can rewrite them as a second order equation. This is simply, this is a well-known equation. You might be familiar with this. This is simply a second order simple harmonic oscillator. This equation resembles that of a simple harmonic oscillator, and whose solution you can just simply written as, so V of t as V naught cos of square root of 1 minus under the root of 1 over LC times t. So this is simply a simple harmonic oscillator where x dot is omega naught square x, whose solution you can give it as a sine and cos, right? So we can simply we can just simply write its solution. And if you look at the solution, obviously this will exhibit just a sinusoidal oscillation, right? So those initial energy which is stored in these elements, the inductor and the capacitor, they keep oscillating back and forth in this circuit. This is called a tank circuit, referred to as a tank circuit. The initial energy stored in these elements just keep on back and forth, oscillating back and forth between these elements, giving rise to sinusoidal oscillations. Now let's introduce a resistor over here. And again, after using the Kirchhoff current and voltage law, so we can write these equations. And again, just clubbing them together, you can re-express them as a second order equation of this form. Okay, so now we have damping term here. In addition to these two terms, the first and third term. So in the previous case, because of the introduction of this resistor, we have a damping term over here. Okay, so now the behavior of this equation, right? So with the damping, so depend upon the value of R, whether R is less than or greater than 2 times under root of L by C. So depending on this, we can write solutions. So when R is less than 2 times under root of L by C, one can deduce the solution of this form so less than, we can deduce the solution of this form. So now, so this beta delta has the appropriate form, which I didn't included over here. You can refer to Lakshman and Rajshekhar book for these things. So if you look at the solution, right? So this exhibit a periodic sinusoidal oscillation, whereas this will exhibit exponentially damped oscillation. So the combined effect of this exponentially damped solution and also this sinusoidal oscillation results in damped oscillatory solution whenever R is less than this quantity. On the other hand, so when R is greater than this factor, then it corresponds to the overdamped case. In this case, we have a solution of this form. So we have exponentially damping solution. This term dominates, and hence we have exponentially damped out solution here for this case. And this case is a overdamped, and this case is referred to as underdamped case, where one can have a damped oscillatory solution. Whereas in the case of overdamped case, we have the exponentially damped solution. So now what we are going to do, we are going to include a forcing term, including an external forcing into the circuit, so that we have an LCR circuit with an external forcing with a suitable frequency. So now again, applying Kirchhoff current and voltage law, you can write the equations across the capacitor and inductor as this form. So then you can re-express them as a coupled to second order differential equation. So in addition to this damping, now we have an external forcing with frequency omega with appropriate amplitude here, right? So now what would be the dynamics that you could expect now? So without the forcing, when F is 0 here, so we have damped oscillations. Damped oscillations are exponentially damped solutions depending upon the value of R. Anyway, we have asymptotically we have damped solutions. The initial energy stored in the inductor and the capacitor will dissipated out as a heat across the resistor. So now we have a sinusoidal forcing in it. So in addition to the damping, right, damped solution, we have a periodic external forcing into it, and which is expressed in its solution. So in addition to this damped oscillatory solution, in this case, so we have external periodic forcing. So now, so the waveforms, the current and voltage waveforms in the inductor and the capacitor respectively, right? So they will exhibit sinusoidal oscillation with frequency which is resonant with the frequency of this external forcing, and eventually we have a closed orbit looking like an ellipse in its phase space. Okay, and this is the asymptotic. This is the most general asymptotic behavior or solution one can expect from this linear forced system, right? So next, we will move on to the nonlinear circuit. So I just, as an example, I take here the Murali Lakshman Chua circuit. So in addition to the quantity or whatever be the term that we have discussed, we have a nonlinear element here. So we have a nonlinear element. Without this element, it is simply the LCR circuit with forcing into it, and whose dynamics will simply an sinusoidal oscillation. So, but now we have included this term, the nonlinear element over here. This is called the Chua nonlinearity. This takes the form. The Chua nonlinearity has this form. You have two operational amp with appropriate resistors are included here. And the current voltage characteristic of this nonlinear element is shown here. And if you look at this, this is no more linear, right? So this is piecewise linear. The current voltage characteristic of this Chua's nonlinear diode is piecewise linear. Here is piecewise linear, here is piecewise linear, here piecewise linear in between these segments minus BP to BP, right? And altogether, it is a nonlinear form. Altogether, the function, the function took nonlinear form. So we usually refer to this as a piecewise linear. So we have a nonlinearity. Now we have a nonlinearity included into the LCR circuit with forcing. Now let's check it out. So what would be the dynamics? What would be the dynamics exhibited by this system as we include the amplitude of the external forcing? So again, applying Kirchhoff current and voltage law across the whole capacitor and inductor, one can write the equations of this form. Again, you can couple them. You can write a couple second order equation. So the nonlinearity is given here as a function h of v, where h of v has this piecewise form. So this behaves like this. This is a linear in this region. Again, it's a linear in this minus BP to BP. Again, it has a linear form in this region. So overall, it is a nonlinear function, right? So now, so in the earlier case, without the nonlinear element, we have seen only sinusoidal oscillation as the most general behavior, which is the most asymptotic general behavior exhibited by the system. But on the other hand, by including a nonlinear element and by changing the value of the external forcing, amplitude of the external forcing, we can have different types of behaviors. So, for example, as an example, I have shown here just only the period doubling cascade scenario leading to chaotic attractor, single band and double band chaotic behavior, chaotic attractor. There exist vast other dynamical behaviors like intermittent and so on, and the various types of intermittent, quasi-periodicity, and so on. So here I have shown, as an example, I have shown just the cause of the period doubling route to chaos. And for, I think this is for f equal to 0, this exhibits just a steady state. The equilibrium point is stable here. Just it is an equilibrium point. It's a fixed point. So steady state is stable, and the system doesn't exhibit any other behavior for the chosen values of the parameters. Upon increasing f to certain value, it exhibits period of oscillation. Then increasing the amplitude of the external forcing, which I referred as f. So this period get doubled, resulting in a period doubled oscillation. Okay. So now, upon further increasing the amplitude of the external forcing, it doubles further, resulting in a period 4 oscillation. And further increase in the value of the amplitude of the external forcing leads to further doubling, basically 4 to 8, then 8 to 16, then 16 to 32, and so on, and eventually above a critical value, ending up in a chaotic attractor of this form. And this is a single band chaos for suitable initial condition, and this is one can also have a single band chaos of only in this area. And this is for further larger value. I think this is FS 0.42 something. We have a double band chaotic attractor. The system exhibit the double band chaotic attractor for appropriate value of the external forcing. Yeah, actually, this is a representative picture. Basically, this dynamics is exactly the dynamics of Chua circuit or not of MLC circuit. Just this is a representative one showing the period doubling cascade to synchronization, to chaotic behavior. Yeah. So now the dynamical system can be further classified as autonomous and non-autonomous system. So the system that we have discussed so far, which is the MLC circuit, is simply an is a non-autonomous system because it has an external forcing. So here it is an example for autonomous system. So where it does not have any explicit dependence on time. So such systems are classified as an autonomous system. If the system has explicit dependence on time, then such systems are classified as an autonomous, non-autonomous system. And here, as an example for autonomous system, I took the Lorentz system. These are the parameter values. Basically, this system refers basically constructed from atmospheric fluid model. This is a celebrated butterfly attractor of the Lorentz system for this choice of parameters. And as a non-autonomous system, here I just took as an example the Fink oscillator. Here we have an explicit dependence of time on such systems are referred to as non-autonomous system. And as an example, I took a Duffing oscillator where we have the external forcing. So whenever the system has external forcing, then we call it as a non-autonomous system with certain frequencies. And these are for this parameter choice. And here is a double band attractor of the Duffing oscillator.
Bhagiraj, do you have some doubts, Bhagiraj? Excuse me. Bhagiraj, do you have some doubt? You want to raise some questions, or you can mute? Yeah, please. Sorry.
Yeah, shall I continue?
Yeah, Bhagiraj, you want to talk something? Okay. Yeah. Sorry, Sanjay. You can continue.
Since I am sharing my screen, I cannot see. If you raise your hand, I cannot see it. So probably we will check it out at towards the end.
Okay.
And if you have any,
excuse me, Sanjay, you want to take the question then and there, or you want to take the questions at the end of your talk?
It's anything. Anyway, it's fine. But
okay, if someone raises their hand, then I will intimate you. Okay.
Yeah. So otherwise, I will, after finishing the first part, we will go for the questions. Then we will, after finishing the second part, we'll go for the questions.
Oh, okay. Okay.
Yeah. Okay. Yeah, that would be good, I think. So otherwise, would be enough. Yeah. So we classified again the systems as autonomous and non-autonomous, depending upon whether it has explicit dependence of time or not. So now again for the system. So I already discussed. I showed you right for the circuit. So which exhibit a fixed point behavior, a fixed point. For some values of the forcing, it exhibit a fixed point oscillation, whose phase trajectory will look like this, and whose time series will look like this. This will oscillate and finally settle into the steady state. And whereas this is the period 1 behavior, whose phase trajectory would look like this, and whose time series will look like this. And here is a period 2 oscillation, and the phase will look like this one. And whereas this time series is plotted here. And further doubling, it's period 4 behavior. This is a period 4 attractor, and this is again a single band chaos and double band chaos of the Duffing oscillators, and whose time series are plotted over here. One can also simulate in order So one can also look at the circuits and look by varying the parameters. We can look at the dynamical changes through CROs. One can also solve these equations numerically. And by varying the parameters, we can plot the dynamics on the phase space, and also as a time series, we can visualize the dynamics by plotting them for different values of the parameters either in the phase space or as a time series. So this is the attractor, the double band attractor of the Duffing oscillator, and here it is a Poincare section. So if you take, we have external frequency, right? Just if you take 1 point per cycle. So just if you just take 1 point for, I will just maybe stick to it, it will be easy. So for 1 cycle, if you collect just 1 point, right? And if you collect the points like that, so for example, if for a 1 cycle, if I collect only the maximas, right? I will always be collecting only the maxima. And if I plot this value, whereas the x value here would be some fixed value. And similarly, the corresponding maxima in the y variable will be also a fixed value. If I plot those things in the phase space, then I'll be getting just only a 1 point. This is called stroboscopic picture of this attractor. This attractor in 2 dimension can be reduced to 1 dimension by looking at its Poincare section. So that this the 2 dimension space can be reduced to 1 dimension. On 1 dimension, the same period 1 orbit can be represented as just 1 point. Similarly, if you take Poincare section for this period 2, we will have period just 2 points in the phase space. And for period 4, obviously, you will have period 4 points in the phase space, and so on. And eventually, for a chaotic attractor, you have a structure like this. So this is a nice structure for this Duffing oscillator, double band Duffing oscillator. But basically, you will have scattered points all over the phase space. And this is for a specific value of the parameter. Okay, so this is for the specific value of the parameter. Now, if we plot the Poincare section, as a function of the parameter in the entire range, for example, if I just vary the amplitude of the external forcing from this point, from fixed point, or from periodic orbit, and if I just scan, if I take the Poincare section for all these orbits in the entire range of the control parameter, which is amplitude of the external forcing here, and if you plot it, then we plot the Poincare points as a function of the parameter, then we call it as a bifurcation diagram. So this gives the global picture of the dynamics exhibited by the system. So now what we have visualized earlier is for specific value of f, we have plotted their phase space, and we have also plotted the time series. And we just looked at the period 1 orbit and period 2 orbit, period 4 orbits, and so on and so on. So now we have captured the global dynamical behaviors in terms of bifurcation diagram. So bifurcation is defined as a sudden qualitative change at a critical value of a parameter as you scan the parameter. So now you see this is the bifurcation. Bifurcation happens here, where period 1 bifurcates into period 2 behavior. So there is a sudden qualitative change in the dynamical behavior at the critical value of the parameter as you scan the parameter. And this is how the bifurcation is defined. I repeat, the bifurcation is defined as a sudden qualitative change in the dynamical behavior at critical values of the parameter as you scan the parameter. Okay, and hence this diagram is called the bifurcation diagram. Okay, and this gives the global picture, global dynamical aspect of this is one parameter bifurcation diagram. Similarly, we can also have a 2 parameter. You vary one more parameter, and you can also plot the two parameter bifurcation diagram. This is basically one parameter bifurcation diagram, giving a global dynamical picture. Exhibited by the dynamical system. By looking at this bifurcation diagram, you can clearly state that in this range of parameter, the system exhibits period 1 attractor, and in this range from here to this value, the system exhibits period 2 attractor, and here the system exhibits period 4 attractor, and so on. Right. So this gives the global aspects, in the entire range of this parameter. We can say that so this is the range of parameter, and given if you ask what is the value, what would be the dynamical behavior at f equal to, for example, 0.36, by looking at this bifurcation diagram, you can say that this will exhibit chaotic attractor. And this gives us the global view about the different types of dynamics exhibited by the system as a function of this parameter, chosen parameter. You can choose any other parameter. Similarly, you can plot bifurcation diagrams, and you can also plot the same diagram as a function of 2 parameters, where you can see the dynamical behavior for those choices of those 2 parameters. Okay, so now so we have seen chaos. We have seen now integrable, non-integrable systems, and we have discussed that this exhibit period doubling cascade to chaos, and we have some exposure to chaos at the moment, right? So now, what is chaos? So chaos is defined as aperiodic, non-periodic, and it should be bounded, but having extreme sensitivity to initial conditions. This extreme sensitivity initial condition is defined as a hallmark property of the chaos, which is being utilized for quantifying the chaos using Leopold exponent. Before that, so this is a non-periodic bounded. See, its phase space is bounded. You look at the range of x, right? It is bounded. Also, if you look at here also you can say that it is bounded in this range of x. Right? Look at the phase space of the chaotic attractor. It is bounded, right? Bounded in the x and y axis. So it is bounded motion, but it is an aperiodic bounded motion and have extreme sensitivity initial condition. And the extreme sensitivity initial condition is shown here. See, initially, so the different initial condition is at the 5th decimal point. Okay, so it's at the 5th decimal point. This is negligible difference in the initial condition. See, even though the initial condition, the rest of the parameters are fixed. The same parameters, only change is a change in the initial condition at the 5th decimal point. So you can see that initially there is no change. You cannot see any difference initially, but after some finite time, after some finite time, these two trajectories diverge exponentially away from each other, right? They diverge exponentially away from each other, and so and this illustrates the initial sensitivity to initial conditions, sensitive dependence on initial conditions of chaotic trajectories. And this is referred to as a hallmark property of the chaos, which is being utilized for quantification of the chaos using Lyapunov exponent. So now, and we have other type of characterization like power spectrum and so on, like working out the dimensions and so on. And this is a more prominent one and quantification measure, which is being widely utilized to identify the chaos. So the Lyapunov exponent here. So this is delta I is basically the Euclidean distance. You can have two-dimensional system or three-dimensional system or n-dimensional system. So depending upon the number of variables the system has. So this is the difference between the initial condition, difference between the two. Yeah, maybe I'll come back. Yeah. So basically this delta I of t is the difference between at some t, difference between the trajectories at some t. You can consider at t at this point, so that the difference between the trajectory evolved as like this here, and difference between this point and this point. So whereas delta I at 0 is the difference at this point. Okay, so difference between the trajectory at this point at t equal to 0, and delta I of t is the difference between the trajectory at some finite time t. Okay, let us consider at this point. Okay. So now the difference will the deviation between the trajectory will evolve in this fashion. So now from this, the Lyapunov exponent lambda I, which is the Lyapunov exponent, can be written as this fashion. In terms of just rearranging, you can recast this into this form. So as t tends to infinity, right, in the asymptotic limit, in the long time average. Okay, so this gives the quantification measure. So by looking at the maximal value, largest value of lambda I, you can have this I runs from 1 to n, where this 1 to n corresponds to the number of variables that the system has. Okay, for three-dimensional system, this I runs from 1 to 3. We have basically 3 Lyapunov exponents. Now we look at the maximal. If you just reorder them, you can have a maximal Lyapunov exponent. Okay, so just arrange them in ascending or descending order. You can have let's check only at the maximal Lyapunov exponent, and let's decide about the dynamics or nature of the dynamics. So okay, so in the case of chaotic orbit, right? In the case of chaotic orbit, if you look at it, they exponentially diverge. So at some time t, after some time t, this delta t, right? This is greater than delta t at t equal to 0, correct? So basically, this is the numerator is greater than the denominator, right? So then this term, the term within the bracket, the log, right? This term is greater than 1. Hence, log of some quantity which is greater than 1 is a positive quantity. Okay, on long time average, such long time average will be taken, and this will lead to a positive number if the trajectories exponentially diverge away from each other. Hence, the positive value of the maximal Lyapunov exponent, quantifies the chaotic nature of the trajectories. On the other hand, if this delta I remains the same as this, delta I at t remains the same as delta I of 0, which means it neither diverges nor converges, right? So then in this case, they remain same, right? So then this is 1, right? The different distance is same, and hence this is 1. Log of 1 is basically 0, and hence if the maximal Lyapunov exponent takes a value 0, then this corresponds to the periodic orbit. So if you look at on the periodic orbit, whatever be its period on the periodic orbit, right? So after initial transients, so it will stay ever on the periodic orbit. It will stay ever on the period. It neither converge to some fixed points is say here, or it neither diverges away from the fixed point here. It always just going on the periodic orbit. So it neither converges nor diverges. Hence, the largest Lyapunov exponent is 0. So then the corresponding dynamical behavior is a periodic orbit. On the other hand, if you just look at this behavior, I have taken the initial condition here, and if you look at some initial condition here, then it exponentially converges. If I took some different, one more initial condition, maybe some other point here, which is different from here, and this being damped oscillations ending up at the stable steady state, right? And this will converge, right? This is the initial difference will just eventually fade away and converge to the steady state. So in this case, the initial difference will be greater than the final difference, and hence, this will be numerator will be less than the denominator, and hence this quantity will be less than 1, but positive number less than 1, which the log of a positive number less than 1 will be a negative quantity, right? So this if the maximal Lyapunov exponent acquires a negative value, so then this characterizes the fixed point. Okay, so we can state that if this is very important, no doubt, if the largest Lyapunov exponent is negative, okay, so then we can state that the dynamical state is a steady state, stable steady state. Okay, it doesn't exhibit any type of oscillatory behavior. It is a steady state behavior. Okay, so for hyperchaotic attractor, we have more than one positive Lyapunov exponent. This means that it has more than one direction, diverging directions. If it has more than one diverging directions, then it is characterized by more than one positive Lyapunov exponent. Hyperchaotics are characterized by more than one positive Lyapunov exponent. Okay, so now we have discussed about on period doubling cascade to synchronization. We have also characterized period doubling cascade to chaos. Then we have also discussed about characterization of chaos using Lyapunov exponent. We have also discussed what does the maximum value of Lyapunov exponent illustrate about the dynamical nature of the system, right? So depending on the value of the maximal Lyapunov exponent, now we could able to classify the nature of the dynamics exhibited by the dynamical system under consideration, right? Yeah, here is a Lyapunov exponent. Here's a pictorial representation of a Lyapunov exponent. Here you can clearly see, right? So this is the bifurcation diagram. So where you can know you are already aware that this is a periodic behaviors until this point, and this is a chaotic behavior. And as we have discussed, right? So this is a maximal Lyapunov exponent. Here, two largest Lyapunov exponent are plotted here. Two largest Lyapunov exponent are plotted here. Just look at the maximal Lyapunov exponent here. So for the periodic orbits, these are just the maximal Lyapunov exponent is 0 here, and the maximal Lyapunov exponent tends to be positive here. The chaotic orbits actually basically starts from here. So this shows that the chaotic orbits are characterized by positive Lyapunov exponent, and this in between they have periodic windows. The periodic windows, right? They have dips over here. This illustrating the periodic windows here, periodicity of the dynamic behavior at this point. And this we call as a Lyapunov spectrum. Yeah. Okay. So now just let's get back to this Lorentz system, right? Which is an autonomous system. So now let's look at the equilibrium point. Let's work out the equilibrium point, and let's work out the stability of this equilibrium point by using the linear stability analysis. So we are looking at the equilibrium point, right? Which is mean the fixed points. Equilibrium points are nothing but the fixed point. If the fixed points they are fixed, right? The points are fixed. Hence, it should not evolve with respect to time. Hence, in order to extract the fixed point of the system, you have to substitute x dot, y dot, z dot to be 0 because they are fixed points. They are not going to evolve, right? So we have to substitute x dot, y dot to be z dot to be 0. Then this will result in x star as y star, and you can similarly write this things. This star basically, we denote it as at fixed points. And if you solve this equation, solve for x, y, z, we can get 3 equilibrium points. One can get 3 equilibrium points for the system, and the equilibrium point. This is a trivial equilibrium point, which is the origin. And this is the non-trivial equilibrium point, which depends on the value of beta and r. For r less than 1, if you look r less than 1, and this become imaginary, right? So the origin is only the equilibrium point in this case for small r less than 1. R less than 1. Otherwise, for r greater than 1, we have 3 equilibrium points basically here. Now, yes.
Where comes this B?
So B, yeah, sorry, B is beta here. Yeah, misrepresentation. Yeah, B is beta here, right? Yeah. Yeah. So we have 3 equilibrium points here. Now we got the equilibrium point. Now we need to determine whether it is stable or unstable. Okay. So how to determine the stability of the equilibrium point? Now we have x star, y star, z star as 0, 0. Let's just stick to this equilibrium point, E1. So now substitute back. Yeah, before that, what to do? So we have to work out the Jacobian of this system, right? So Jacobian is simply, if you write this x dot as function f1 of x, y, z, and y dot as f2 of x, y, z, and z2 as f3 of x, y, z. Jacobian is nothing but the matrix which is derived from. So this is dou f1 by dou x, dou f1 by dou y, dou f1 by dou z. Similarly, this is dou f2 by dou x, the partial derivatives of this function f2 with respect to x, y, z, and partial derivative of the function f3 with respect to x, y, z. Those are these elements of this matrix, and which is subtracted by minus lambda I, Jacobian minus lambda I. Yeah, so if you just look at it, so if you take derivative of this with respect to yes, this is sigma, right, plus sigma. Whereas if you take derivative, partial derivative with respect to y, this is just minus sigma. So you can, and with respect to y, but there is no z term, so it should be 0. So you can see that is what reflected here. And this Jacobian minus lambda is being shown here. And if you work out the equilibrium point, and if you substitute x star, y star, z star to be 0 here, and this is a if you substitute x star, y star to be 0, and this will reduce, this will simplify our life, and we can write the rewrite this matrix. And if you write the eigenvalue equation, if you solve the eigenvalues, these eigenvalues will show you so whether the equilibrium point, the trivial equilibrium point with its origin is stable or not. So when it is stable, if the largest eigenvalue is going to be negative, if the largest eigenvalue is going to be negative, then rest eigenvalues will follow. They are also going to be negative. If the largest eigenvalue is negative, so then the equilibrium point is stable. If at least one of the Lyapunov exponent is positive, which means the largest Lyapunov exponent is going to be positive, then we can assert that the equilibrium point is unstable. Okay, this is a general eigenvalue equation, and where the parameters are the A1, A2, A3, these coefficients are written in terms of those parameters of the system. So by substituting these appropriate eigenvalues for x, y, z, one can able to determine this, arrive at the eigenvalue equation for the corresponding equilibrium point, and one can, by solving the eigenvalue equation, one can determine the stability of the corresponding equilibrium points. So I reiterate, the corresponding equilibrium points are stable if the corresponding maximal eigenvalue is negative. Otherwise, it is unstable. Okay, and this is for a single system, and this is the case for the single system. And in case if we have two such system, I am taking a copy of this. Let's take x1, y1, z1, and I will represent similarly one more copy of this as x2, y2, z2. And if they are coupled with some fashion, okay, if they are coupled with some fashion, now we have a coupled system, two coupled systems, right? So now one can also do the stability analysis of the coupled system with 6 variables. Right? Now we have a coupled system with 6 variables, and one can also do the similar analysis, follow the same technique. One can also arrive at the eigenvalue equation for the 6 variable system. Okay, and one can also solve. So if one can manage to solve the equation, obtain the corresponding eigenvalues, so then one can determine the stability. One can show the stability of the one can discuss about the stability of the fixed points exhibited by this coupled system. So we have two systems, they are coupled to each other, and they also have equilibrium points, right? They also have equilibrium points. One can again determine the stability of the equilibrium points following the similar technique, similar prescription. Okay, for this is important because I am going to discuss about the amplitude depth, oscillation depth. So those occurs when the systems are coupled. When the oscillatory systems are coupled together and beyond a certain coupling strength, their oscillations get mutually suppressed. The oscillations of the two systems get mutually suppressed above a critical value of the coupling strength, leading to the fixed point solution, leading to the steady state solutions. And this steady state could be a new steady state, or it could be the steady state already existing in the system. Okay, so when two systems are coupled, beyond a coupling state, this oscillatory system mutually suppress their oscillation, leading to the steady state behavior beyond the critical coupling state. Such transitions are called oscillation quenching, which we are going to discuss about it shortly. And the same prescription we are going to deal with. Yeah, and also whenever I speak about reviving oscillation, we have just couple system over here. Instead of one system, we have couple system here. We do the same prescription to determine the equilibrium points and their stability. Okay. Yeah. So now, now we have coupled systems. Now we have coupled system, and the coupled system, if both we have two systems and two systems settle into the same fixed point, it is called homogeneous steady state. Same fixed point, same steady state, homogeneous steady state, which is nothing but the homogeneous steady state. Then under coupling, so then such steady state, homogeneous steady state are termed as amplitude depth. Okay. On the other hand, if the two coupled systems settle into the different steady state, look at here. System 1 is settled into one steady state, and system 2 is settled into a different steady state. This we refer to as inhomogeneous steady state. Okay, inhomogeneous steady state. Then such inhomogeneous steady state, which is induced under coupling, is called oscillation depth. Okay, so this is the suppression of oscillation, mutual suppression of oscillation under coupling, which is referred to as the phenomenon of quenching of oscillation, which is being further classified as amplitude depth and oscillation depth. And they have a different manifestation. Usually the amplitude depth does not lead to any symmetry breaking bifurcations, whereas oscillation depth normally arises through symmetry breaking bifurcation, basically from pierce through in homogeneous steady state through inhomogeneous steady state via Turing bifurcations. Okay, so the quenching of oscillation now classified as amplitude depth and oscillation depth, which are nothing but the homogeneous steady state and inhomogeneous steady state, which arise out of the oscillating system under coupling. Okay, when you remove the coupling, the systems are under oscillation. They are oscillatory systems. But when you introduce the coupling and beyond the critical coupling state, they exhibit this kind of behaviors where the coupled system mutually suppress their oscillations and leading to the steady state behavior. And note that again, the steady state could be the existing steady state in the system, or it could be a new steady state created due to the coupling induced steady states. Okay. So now, so there are ample of literature available on this amplitude and oscillation depth through a variety of coupling scenario. I refer you to this recent review, our recent review. Yeah. So once substantial understanding about the oscillation amplitude depth has been carried out, so then people started looking at the amplitude to oscillation depth, which I refer to as a Turing bifurcation here, right? So which basically appears through symmetry breaking bifurcation. Here the system is symmetry, where here the symmetry has been broken. Symmetry of the dynamical states has been broken here. So it appears, usually this OD appears through the symmetry breaking transformation. Here, basically this plot shows time delay induced AD to OD transitions. So after a certain time, when AD and OD has been well understood in the literature, again, researchers' interest has turned towards identifying this AD to OD transition through symmetry breaking bifurcations. Here it is specifically because of the delay induced. If you see tau here, tau is the delay here, and delta is the frequency mismatch. So in the absence of delay, there is nothing, right? So the dotted lines are unstable steady state, where solid lines are stable steady states, right? Here it is the OD state. You can see here in the right column, it is a delay. There is a delay is there, okay? For increasing value of the frequency mismatch here. Delay is there for increasing value of the frequency mismatch. So this illustrates that delay on the frequency mismatch induces the transition from AD to OD. And at some part of, at some time during last decades, there vast amount of literature publications has been appeared on this AD to OD transitions. And there is one more transition, one more dynamical phenomena called aging transition. Here, so we refer, so basically, yes, this amplitude depth and oscillation depth, or transition from amplitude to oscillation depth, or even explosive depth has been reported in the literature. So this dynamical states, this phenomena, amplitude depth, oscillation depth, these transitions among the oscillation, amplitude oscillation or explosive oscillation depth has been identified from 2 coupled to n coupled systems. Also with frequency mismatch and distributions of frequencies, various distribution like Lorentzian, Gaussian distribution of frequencies among the system. And it is also identified in arbitrary networks with arbitrary topologies. Okay, and also with complex networks with weighted coupling, frequency weighted coupling, or weighted with degree distributions and so on. Vast amount of literature again with various heterogeneities exist in the literature, where we have given a exhaustive review in this review article. So there is a one more dynamical transition which leads to suppression of macroscopic oscillation of the entire of an ensemble of systems. When we consider n number of systems, right? So there is another phenomena which leads to the suppression of the macroscopic oscillation of the system, and that this phenomena referred to as the aging transition. Here, the difference between the previous case and the here in this case is here they introduce so among the ensemble of oscillators, they introduce active and inactive oscillators, whereas in the earlier case, there is no such active separation of active and inactive oscillators. So all our oscillator states, oscillatory systems over there in the previous phenomena of amplitude and oscillation depth or explosive depth, so on. Here, so in an ensemble of oscillator, we have 2 groups of oscillator, where one group is an inactive oscillator, means they are exhibiting only steady state behavior, and there is another group of oscillator which is an active oscillator exhibiting oscillatory behaviors. Okay, so now if we increase the fraction of inactive, the P here corresponds to the fraction of inactive oscillator. If we increase the fraction of inactive oscillators above a critical fraction of inactive oscillators, the macroscopic oscillation basically suppressed, leading to the dead state, leading to the loss of macroscopic oscillation, which is referred to as aging transition. Basically, yeah. So while this phenomena has been introduced, they refer this, they focus as an application to the neuronal state, where where this aging phenomena and increasing the number of inactive oscillators being referred to as inactive neurons. As we go on in our real aging process, right, so the neurons going to be die out, and as the large number of neurons are going to die out, so we have a large proportion of inactive neurons over there, which leading to memory loss kind of disease. They try to correlate this phenomena to those applications to understand those aspects, biological phenomena. Okay, and this is the order parameter. Q is nothing but the order parameter which quantifies the macroscopic oscillation. When P is 0, the ensemble comparisons of only active oscillators. When P is 1, it's completely inactive oscillators, whereas the intermediate values corresponds to the proportion of active and inactive oscillators. And this phenomena of the loss of macroscopic oscillation, occurs at critical value of P. If you increase the fraction of inactive oscillators, at a critical value of P, the macroscopic oscillation get losses, which also gives some information. About the robustness of the network. People also have addressed this PC, the critical value of PC, as quantifying the robustness of the network under consideration. Okay, and with this brief introduction to aging, amplitude depth, quenching of oscillation and aging transition, I'll move to the second part of the talk. And before that, now I think we can go for any doubts and discussions if you have.
Okay, if someone has a doubt, they can raise their hand, or you can unmute and raise the question.
Sindhil, you have given a very nice introduction. I really enjoyed it. Can you go to the last slide?
Yes.
Yeah. So, is it surprising that when the number of inactive oscillators are large, then the entire system gets
Yeah. So when So when so when P is 1, then the ensemble comparisons of only inactive oscillators. So in this case, it is not at all surprising. But when there is a proportion, in some cases, right? So even a small proportion of inactive oscillators can lead to the loss of macroscopic oscillations. So that depends upon the coupling strength here. Coupling strength. Is this fine? Did you hear me?
No, we are not getting. Sandil, I think we are not getting a response.
Yeah, so maybe he may have some network issues. I don't know. Yeah, so maybe until he arrives, maybe we'll.
Yeah, are you able to hear my voice, Sandil?
Yes, I'm hearing you.
Maybe downstairs. Yeah.
Yeah, if you have any other questions, we will engage others until he appears. He come back.
Yeah.
See.
Yes, I think Chandrasekhar has another doubt.
So nice presentation. So I have one basic question. Yeah. So in slide number 30.
Yeah. Slide number. All right.
Okay, so to quantify the nature of the orbit, here we use the concept of exponential divergence.
Yeah.
Okay. So my question is exponential divergence true for all chaotic systems?
So
and
classical, for all classical systems.
Yeah, it's true for all chaotic systems.
Classical systems, right? It should be.
So for all
because the chaos is
different. For linear systems, the damping is the exponential. Okay, so we use the concept of exponential damping and so on. But if you go for the nonlinear system, even if the highly complicated nonlinear system have the many more stable orbits in the given single parametric choice, I think the exponential divergence is not a valid assumption for that system.
So here, so if you have other stable orbits, right?
Yes.
This will have its appropriate values. So when come to chaos, the chaos is defined as an exponential divergence of nearby trajectories, right?
Okay.
For characterizing classical chaos, that exponential divergence, without doubt, this captures that degree of divergence.
Suppose I have a system, but the chaotic orbit not exponentially diverse. So in that case, is it possible? Since most of the some nonlinear systems have the multi-attractors or multi-stable nature, if I choose the initial condition between the two attractors, in that case, the exponential divergence is not
assumption. We are struggling, right? So for our work, if we have multi-stable attractors, we cannot able to
if you choose the initial condition in the two different attractors, but the exponential divergence is not possible.
So in 3 to 4 different cases, in different works we encounter that we cannot able to compute the Liouville exponent for those systems if we choose initial condition of different attractors.
This is valid only for if you choose the initial condition in the same attractor.
Yes, exactly. Right, you are right.
So,
yes.
Most statement we have to add.
Yes, it cannot be general. That has to be made clear. No, I got your point.
Any other question from the audience? Okay, if not, you can continue. Sir.
All right. So then we'll move on to the second part of the talk. Since I have already given an introduction to AD amplitude quenching state and transition from AD oscillatory, amplitude depth oscillatory state, and also aging transition, I will just focus this part of the talk mainly on reviving of oscillation by just showing up, discussing results of our recent publications. And I have the audience might be aware of networks, right? So networks are classified as a regular network and complex network depending upon the topology. So if there is a regularity in their connection, so then such networks are classified as a regular network. For example, if you look at here, there is some degree of regularity in their connections. So this such networks are classified as a regular networks. And here is that again, I have given two physics reports here, which reviews which are exhaustive review on basics, fundamental aspects of network theory, and also dynamics on and dynamics of networks, including synchronization and various kind of things, starting from cluster states and so on. So one of the audience, if they are interested, someone can refer to this references for further details. And again, yeah, once we have regular network, then we should have a different type of network, right, which is called complex network. See, so the complex network are again classified as a regular, small world, random, scale-free, and so on. So we start with, so how do we construct? We start with a regular network. We rewire this, rewire it with some probability P. And if we keep on rewiring this with some probability P, we eventually transit from small world network to random network. Okay. Yeah, so this is how one construct the random networks of different networks, small world, random, small world or random network. And this, again, these networks can be characterized using several quantification measures, such as the shortest path length, clustering coefficients, and degree distributions. For example, if the degree distributions, so they show power law, then such networks are classified as scale-free networks. And we have other types of network, hierarchical network. Further details, I ask you to refer to this physics reports. And so now the point here is there are networks there are networks, and networks are classified as a regular and complex networks. Okay, yeah. So there are also, in reality, there are networks. These are not just abstract networks. In reality, there are networks. So can can you think of any network? So look at so the transportation network, right? Railway network, or railway network, or road transportation network, or air traffic network. They form a they are part of class of a networks. Then if you think about neural network, several biological networks such as neural network, metabolic network, and so on. For the social networks such as mobile network, right? WhatsApp or internet, authors collaboration network. So where you look, there are ample of examples around us in the real world where networks are there, and power grids, for example, power grids are network, logistic network, right? So networks are everywhere in the real world, and different types of networks are indeed there. Huh? Okay, now what is a great deal of network? Yeah, so this is a real map of power map of southern region. Yeah. And here is a neural network, which is again classified as a structural network, functional network, effective network. Yeah, again, a couple of references where you can have more details on the networks. Okay, so yeah, so before proceeding further, I would like to show you one real network. So this is a one-day air traffic network in Europe. This is real data. Huh? So this is a real data has been collected. Number of flights coming in and going out. And there are peripheral nodes. If you look, there are hubs, right? There are hubs at Frankfurt and so Berlin, Paris, there are Amsterdam. So there are hubs. This is a real world, real network, real complex, evolving complex network. Okay, so there are several such networks out there in reality. This is just to give you an impression of how a real world network look and how it evolves. Okay, so now what is a great deal of network? So now, so whatever be the network that I have said right now, informed you right now, they have their functionalities, right? So power grid, it has to transmit power, right? Logistic network, it has to transmit, it has to supply the logistic, right? One neural network, whatever be the neural network, it has its purpose, right? It has its dynamics. Okay, right. So with that aspect, and this is the power blackout. in southern India. It happened sometime in July in 2012. So this map shows that there is some power failure at a particular at a specific grid at some point here, and which this power failure at a specific grid cascades to it cascades subsequently, and it results in power failure completely in north and northeastern part of India for almost 2 days. And this incident has been stated in Wikipedia as the July 30 July 2012 blackout affected over 300 million people and was briefly the largest power outage in the history, counting number of people affected, beating the January 2000 blackout in Northern India, which means there was another blackout, right? So these blackouts are quite common in US in 80s. Yeah, so at the time, 230 million people were affected. So the blackout on 31st July is the largest power outage in the history, affecting over 620 million people, about 9% of the world population and half of India's population, spreading across 22 states in northeast, eastern and northeast India. Right. So look at, just think about this current technological world. If there is no power for 1 day, what we could do? Our household will completely get stagnant, right? We can't do anything. If you look at check out at your research labs. If there is no power for a day, if there is no internet for a day, definitely our work is going to be stumbled, correct? And so so this basically this loss of power due to failure of power grid does not only lead to waste of manpower, loss of manpower, but it has also costed human lives at several instances. For example, I think 2018, I think so, there are around 6 patients undergoing dialysis at Pondicherry Zipmer. They lost their life because of the power failures. So there are several such incidents. Every now and then happening leads to result in loss of human lives. It's not only the economic loss, the power failure of the power failure, not only the power failure, but failure of the networks in general can not only leads to economic loss, but sometimes it also leads to human lives, which cannot be recovered back. Okay, so this is the drastic effects of failures of a network. And there is one more case example for failure of a network. This is a gridlock. So this is again real data. So Delhi loses 7 million man hours and rupees 100 crores to traffic jams in span of 30 years. See, right? See that this gives us the glimpse of economic loss that we incurred due to the traffic jam. 6 years. Look, this is the period where a typical executive spends in traffic jam alone in the gridlock the Delhi. If he has 30 years as an average career, if he has 30 years as his service, this among the 30 years, this typical executive spends 6 years just spending time in the traffic jam. Look at the loss, personal loss and loss to the nation, right? So, and this is more, this become much worse if this person travels from Gurgaon or Noida, if the guy commute, what happened? Yeah. So this figure goes much worse. If the guy commute all the 5 days for the work, for his or her work, the figure could go up to 8 years, right? So this illustrates and this is an example which illustrates the loss of manpower, right? Okay, again, this has been projected in some positive sense, but this is the worst gridlock happens in China. So Great Crawl of China, vendors minted in 60-mile traffic jam that lasted, minted cash was in 60-mile traffic jam that lasted 11 days with no end in sight. So this is projected in some positive sense where the vendors has minted cash, but think about yourself struck over in a traffic jam of 60 miles for 11 days at a point, right? Think about your life, right? Yeah, so these are the consequences of failures of a network. And there are several other instances of network failures. For example, crashing of e-servers. So on the day of Bahubali release, when everyone tried to book their tickets, the servers get crashed. And similarly, crashing of e-servers happens every now and then. Share market crashes, failures of internet after severe attack. breakdown of social networks, and brain death resulting in paralysis. These are some of the examples of failures of network. Okay, so so the point I have to convey now is there exists real world networks, and the network real world networks are also prone to failures, which leads to not only economic loss, but it can also lead to human lives. Right? So so from this, so then, so networks not only fails, not only fails irreversibly, but there are also instances, there are also examples where network fails for a while and recovers back on its own. Okay, for example, again, so the epileptic attack could occur. This basically occurs for a fraction of a second, a few minutes, right? In spells. Then the person become normal. Okay. So perhaps I'm having a video. If I think we are going out of time, otherwise I would show you. So maybe I'll show you at the end if you want. Yeah. So then internet also can fail for a while, then recover. Similar thing for traffic network and financial network. So there are also instances in real world where network could fail for a moment, momentarily, then it can recover on its own, right? So now the point is, the point is now we have something to learn from the network. So what causes the network to fail for a while, and what is the underlying mechanism that the networks could recover on its own? If we understand these aspects, right, we could employ back these techniques into the network, which are prone to failures, and we can employ back these techniques back to this network, and we can prevent any further failures of the networks, right? And this is the objective. This is our motive. Okay. So network, the collapse of network, the failure of network can occur in many ways, and the predominant are the structural instability. So so when a nearby city, a new city or new industry comes next to a city, you have to connect the power grids, the power lines has to be extended. When new house has been constructed, power connection has to be given, right? This leads to the structural instability. So this is also a cause for the loss of stability of a given network, which could lead to collapse of a network. And again, a failure of a peripheral node can lead to failure of network. Then abrupt dynamical events, if some war broke out somewhere, then that could lead to collapse of financial market across the world, right? So some extreme events, abrupt dynamical events, can also cause to collapse of network, and there are dynamical transitions in the network would also lead to collapse. And the dynamical transition we here refer to the transition to the quenched state, AD or OD state. So such dynamical transition leads the entire dynamical network to a static state. If the entire nodes of the network become static and there is no information flow across, then the network literally become inactive, okay, which we refer to as a network collapse because of this dynamical transitions. And we are interested in this aspect of network collapse, where the dynamical transitions lead to cessation of oscillation, leading to the death state, which makes the network become dynamical network to which renders the dynamical network to inactive state. Okay, and we are interested in this aspect, whereas there are several other groups working on these aspects, other aspects of network failures. Okay, yeah. So now, let's get back to some history back. So this paper states that we report that for adequate coupling strength, the array is able to synchronize in spite of random delays. Let's leave this aspect. For adequate coupling strength, the ensemble of oscillators is able to synchronize. Specifically, we find that the synchronized state is a homogeneous steady state, where the chaotic dynamics of individual maps is suppressed. Right? So the homogeneous steady state I already referred to as the onset of homogeneous steady state is nothing but one of the quenched state, which is AD, which is right, amplitude death state. Right? So see, now the ensemble of oscillators, which was initially exhibiting chaotic dynamics, they get suppressed to the oscillations. The chaotic oscillations get suppressed to homogeneous steady state. All these oscillators get synchronized to homogeneous steady state above a critical coupling strength for adequate coupling strength. And this is what reported here. And this is where we are interested in. See, so the network can beyond a critical coupling state, the entire network can be rendered to destinated to steady state. It could be homogeneous or it could be inhomogeneous. Whereas the active network become inactive, so that there won't be any further information processing, so that eventually the network is completely dead, static. Okay. Yeah. So I have given some introduction already to the quenching of oscillation. Basically, the quenching of oscillation dates back to the period of Huygens, where he observed sudden silencing of side-by-side placed organ pipes, where these organ pipes mutually suppress each other oscillations, resulting in complete silence. And that was historically the first observation of the phenomena of oscillation quenching. Then later on, this phenomena has been observed in several physical systems like chemical reactions, neuronal oscillators, laser systems, and so on. As I have already discussed, this phenomenon of quenching oscillation has been classified as oscillation death and oscillation death, amplitude death, depending upon their manifestation. And they have their own applications. It's oscillation death and OD state, AD and OD state have their own own applications where we need to avoid the unwanted oscillations. For example, in machine cutting, in tool machine cutting, there exists chaotic oscillation. Those oscillation has to be suppressed if for the smooth outcome of the cutting process. So there, this AD has been required. Whereas OD has been, for example, OD has been identified as a background mechanism for cellular differentiation, where a single cell has been bifurcated into two different cells having two different functionalities. Okay? So at later stage, OD has been identified as a background mechanism for cellular differentiation. And they have their own applications. But however, in our case, in the current scenario, in the current context, so they leads to drastic determinant effect on the dynamics of the network. Okay. Yeah. So again, this AD, right? So there are several scenarios where this onset of quenched states can appear. So this is one of the first first observations, robust theoretical observations, where they showed that. So I just read that statement. We proved that when the coupling is sufficiently strong and the distribution of frequencies is sufficiently large, note that the two conditions: coupling should be sufficiently strong and the distribution of frequency should be sufficiently large. Okay. Under these two conditions, the system undergo amplitude death. So the frequencies are different, right? The frequency distribution should be sufficiently large. So then essentially it implies that the systems under considerations are non-identical system. Okay. So for non-identical system under strong coupling strength, these authors identified the onset of amplitude death. Okay. And this is one scenario. So where the system, where the coupled oscillators, limit cycle oscillators mutually suppress this oscillation, leading to dead state. Okay. So where the distribution of frequency should be sufficiently large. Okay. So then for a long time, it was understood that so the system should have sufficient distribution, heterogeneity in terms of distribution of frequencies for this phenomena to occur. However, at some later point in 1998, so Ramana Reddy et al. Reported that it's not necessary that the system should have a sufficient heterogeneity. So even one can identify such state, onset of the phenomena of amplitude death, even in identical systems without any heterogeneity in the system, but with the presence of time delay in the coupling. The time delay in the coupling, so this is called as propagation delay. Time delay in the coupling is called the propagation delay. By introducing the propagation delay in the coupling, so these authors managed to show that even identical system could results in amplitude death. And you know what is propagation delay? You know propagation delay. I think you would have listened to news, right? News readers. So when news readers ask questions to some news persons in the field, right? The news reader would have asked the questions, completed the question, but still the person in the spot would have shaking his head, hearing his or her questions, and there would be some lag for his response, right? You would have noted it while watching the news, and this is typical example of propagation delay, where the information takes some finite time to propagate from one point to the other point. Okay, so this is again a physical propagation delay, or for specially separated system, the propagation delay is very much an intrinsic intrinsic factor to be taken into account. So these authors managed to show that by introducing time delay, processing time delay into the propagation time delay into the system, so they managed to show that the phenomena of amplitude death onsets even in identical system after a long time. So then, after that, there are several other scenarios. Several other scenarios have been reported, and the most important and interesting one here there is this author, the Cornish, show that the dynamical coupling. So we don't need to have a time delay in the coupling, but on the other hand, even dynamic coupling, which means the coupling itself change with respect to time, evolve with respect to time. The dynamic coupling could also lead to amplitude death in identical systems. So this was shown by this author. And again, again, this set of Indians again showed that by introducing a conjugate coupling. I'll show those couplings in the further slides. By introducing conjugate coupling, these authors able to show that again amplitude could be realized in identical systems. Right? So there are four predominant scenarios so far that I have discussed, which leads to the phenomena of amplitude. One is sufficient disparate frequencies, which means basically non-identical system, but in identical system, in the presence of time delay, and also in the presence of dynamic coupling, and also the conjugate coupling. Okay, these are the four predominant scenarios which facilitate the onset of the phenomena of quenching. Okay, yeah. So now getting back to our work. So what we did in this work is we introduced so-called the processing delay. So earlier I discussed what is propagation delay. It is the time taken by the signal to reach from. This is a processing time basically. Wow, the propagation time. Time taken by the signal to reach from one node to the other end, right? For the spatially separated system. That is the propagation delay. Here we have introduced a processing delay. This is processing delay is nothing but this intrinsic processing time. For example, if you couple two systems of different processing time, so for example, the teacher teaches the same subjects in the same way to a bunch of students, class of students, but each students have their own level of understanding, right? So they take their own time to analyze and digest the stuffs, right? And this is an example of processing time, which causes a processing delay. Yeah, you can also think of if you just go and buy tickets or anywhere, or if you stand in queue for a security check in airport, for example, you would have reached that point, but you would have to wait for some time for you to get checked or for you to receive the tickets. Right, and this is basically the result of the processing time, which we call as a processing delay. Basically, the relaxation time in dynamical system, latent time in epidemics, economics, or class of processing delay. So we introduced the processing delay, and we showed that in all this scenario, whatever I have discussed, showed you. So this processing delay could be able to destabilize the stability of the homogeneous steady state, which is the amplitude death state, at appropriate value of the processing delay, and we can get back the oscillation in the same parameter space where the system suffered the quenched state earlier. Okay, in the same parameter space where the system suffered the quenched state, we can be able to get back the oscillation by introducing this processing delay into the system without altering the system dynamics. The system is the same system. We are not changing any dynamical aspects of the system. Just by playing with the coupling, we managed to change the stability of the stable steady states, whose stability has been onset or manifested due to this different coupling scenarios. It could be either a frequency disparate frequencies, or it could be time delay coupling, or it could be dynamic coupling, or it could be conjugate coupling in all these coupling scenarios. So this just introducing the processing delay in all these coupling scenarios, we could able to show that this processing delay could destabilize the stabilizing aspect of those things, which results in amplitude death. So we could destabilize those stabilizing aspect and get back this oscillation in the same parameter space. So that now the coupled system or the coupled network could get back this oscillation in the same parameter space, and it's now become a dynamic network, right? And we have demonstrated this from two coupled systems to arbitrary network. Yeah, again, this is again describing, yeah. So Professor Sendilvan, if I exit time, let me know, stop me.
You can go 10 more minutes.
Yeah, okay, fine. Yeah, so now let's consider the two coupled Stewart-Landa oscillator. Without coupling, So this is a Stewart-Landa oscillator, and this exhibits stable limit cycle oscillation. And the origin is the unstable steady state. Origin of this system is an unstable steady state, which is unstable, whereas this system exhibits stable limit cycle oscillation without coupling. But in the presence of coupling, when K, for finite values of K, okay, yeah, so this omega is the frequency, natural frequency of this oscillator. And here in the coupling, delta is the processing delay that we have introduced. And tau, this tau is the propagation delay. Okay, we demonstrate the onset of reviving of oscillation for all those scenarios. This is a more general case. And this Mirillo showed that when tau is 0, delta is 0, and the frequencies are different for disparate frequencies, and the frequency of the oscillators are different, they showed under this condition for sufficient frequency mismatch, they showed that the homogeneous steady state is stable, so that the system exhibit amplitude dip. Whereas Raman and Reddy showed that when omega 1 equal to omega 2, which is the systems are identical for appropriate tau greater than 0, right? They showed the onset of this AD in this state in the coupled identical oscillators, coupled identical Stewart-Landa oscillator, and the exact conditions are this one. So when delta equal to 0, when tau equal to 0, which means the both processing or the propagation delay, in the absence of both processing and propagation delay, so the system is found to exhibit amplitude dip. Again, the stability can be determined. So by substitute, we have eigenvalues, right? We have calculated the eigenvalues by so with the eigenvalues, when eigenvalue when the lambda is negative, I referred as the so the steady states are stable. When lambda is positive, the steady state is unstable. That's what I told you, right? So when lambda is 0, when real part of lambda is 0, and lambda in general could be complex, right? So when real part is 0, that corresponds to the critical curve across which the switch in the stability occurs, right? Because when lambda is 0, that is the border. So when we cross this border to the to this side, where it is negative, the fixed points are stable. Whereas when we cross the border to the other side, where lambda is positive, so the fixed points are unstable. So lambda, the real part, when we substitute alpha to be 0, right? So that gives us the critical curve. So one can determine the critical curve, and from which one can determine the stability range of stable where lambda is negative. Okay, this is the stable condition for sufficient frequency mismatch. This is shown by Mirillo in the absence of any processing and propagation delay, and when the systems are non-identical. So in this scenario, in this case, we show by introducing the processing delay delta for even a very small delta greater than 0. We showed that the stability of the steady state can be revoked so that oscillations can be get back in the same parameter space. So by substituting lambda as just I beta, we obtain the critical curve of this fashion, which is minimum of DC plus and DC minus, and which is plotted here. So this minimum, both the curves has been plotted. The minimum of this analytical curve encloses the region of stable amplitude depth. And the shaded region corresponds to the numerical simulation results, whereas those curves corresponds to the analytical critical curves. And see, so by increasing delta, if we increase delta, it is a very small value, right? Even very small value of processing delay, above which there is no dead state, right? For this, see, this is the region where the homogeneous steady state is stable, but beyond this critical value, the steady state loses its stability, and we have completely oscillatory state, right? So so we showed that by introducing a small processing delay into the system, we can revoke the stability of the stable steady state in the case of non-identical system, and we can get back the oscillation in the same parameter space, in the same range of coupling strength, right? So we can get back this oscillation by thereby rendering the network as a dynamic active network, active oscillators. And the spread is plotted over here. This is for a specific frequency mismatch, delta to be 10. Delta is a frequency mismatch between the system, and delta is 10. Here it is shown as a function of the frequency mismatch, and as a function of the coupling strength. The spread is shown here for delta when there is no propagation delay, and this is the range. This is the spread, the entire range where the system exhibits oscillation depth. By increasing delta to very small values, see very small increment, the spread, the degree of spread decreases and eventually disappears after a critical value, illustrating that the result is robust in a large range of parameter space. Okay. And the second scenario is where the Reddy et al. Have shown that when there is no frequency mismatch, in the case of, which means in the case of identical system, but for appropriate delay, which is the propagation delay, they showed the existence of emergence of oscillation amplitude, right? So this is the case here. We have plotted again, this is analytical critical curve. We have plotted this as a function of coupling strength and the delay here. So when delta is 0, so the black curve, this is the region enclosed. This is the region, so where one can observe AD state. But and this is the result shown by the Reddy et al. But by introducing delta, you see, you can small increase in the delta, which is the processing delay. When we increase the small processing delay, so you can see that the spread decreases, and eventually disappears at this critical value, thereby reviving oscillation, getting back the oscillation in the same parameter space. Okay, and this is again in two-coupled system. This is the normalized area. We now just normalize this R as a normalized area. Normalized area is shown here, where this become completely vanished 0 at this critical value. And again, here this is for the conjugate coupling. You see, this is for the dynamic coupling, where this variable evolves. This is uj. Uj has its dynamics. It evolves here. And this is the dynamic coupling. And here it is the conjugate coupling. Conjugate coupling means the y variable of the other system, k system, is coupled to the x variable of the j system, whereas x variable of the k system is coupled to the y variable of the j system. This is the conjugate coupling. Okay. And again, in these scenarios, those authors have showed the onset of AD amplitude depth in the case of identical systems. Okay. And in both these cases, we have shown the effect of delta, and we showed that increasing delta, we can able to revoke the oscillations back by changing the stability of the stable steady state. So this is for the conjugate coupling, and this is for the this is for the other coupling. Yeah, this is for the dynamic coupling. This is for the conjugate coupling. Here, the largest real part of the eigenvalue has been plotted here. You see, when delta equal to 0, enclosed by the black curve, right? And this is the region where the system exhibit death state. By increasing delta, you could for point 1, the range get decreases, and for this critical value, the real part become positive, so that the stable steady state loses its stability, thereby giving back the oscillations in the same parameter space. When lambda is negative, real part of lambda is negative, then the steady states are stable. When it is positive, they are unstable, giving rise to the oscillations back in the parameter space. Thus, it is clear that evident that delta, which is the processing delay, even a feeble value of delta processing delay, destabilize the stable steady state by switching the stability of the stable steady state, giving back this oscillation. And here it is plotted for specific omega, and the critical value of delta is plotted for a range of omega, illustrating the robustness of the result. Again, the similar thing has been plotted here for the case of conjugate coupling. Yeah, so far I have shown the effect of delta in reviving oscillations in AD regions. So there are also systems where exhibit OD, which is inhomogeneous steady state. And here is an example, which is a coupled brucillator. And for this value, this exhibit an unstable homogeneous steady state, where this system also has some intermediate range of K. This exhibit stable inhomogeneous steady state, and which is displayed here. The dotted lines are unstable steady state, whereas the thick bold line corresponds to the stable inhomogeneous steady state. So this line, right, 2, this is a homogeneous unstable homogeneous steady state, whereas this dotted lines are unstable inhomogeneous steady state, whereas this bold line, right, this corresponds to stable inhomogeneous steady states. Okay, so without delta, so this is the range where the inhomogeneous steady state is stable, thereby illustrating the existence of oscillation depth in two-coupled brucillator oscillator. By increasing delta, we showed that the range decreases and decreases further, and if I eventually vanishes at this critical value of delta, right? So see, even in the case of OD state again, which usually appears through symmetry breaking state, which has a different manifestation, right? So even in this case, the processing delay effectively worked effectively, thereby retrieving back those oscillations in the same parameter space by changing the stability of the stable inhomogeneous steady state. So now we extend it to the network of oscillators here, where GJS is a network matrix, okay, and Dij is the degree.
Excuse me, Sendit, shall we wind up in a couple
Yeah,
of
just
minutes?
with this, I'll wind up. Yeah. So this is a network, arbitrary network. Basically, you can yeah, whatever be the network, you can have a from regular to complex network, and this is the result by by one can work out the characteristic equations of this network, and again the largest eigenvalue gives us the lead clue about the stability of the steady state of the network. Yeah, so this rho n basically determines the type of network. So yeah, so those here the steady state is stable when all the eigenvalues have negative real part. Okay, even if one of the row has positive real part, then the steady state of this network, coupled network, is unstable. All the eigenvalues has to be negative for the steady state to be stable for this network. And again, so we have shown the stable steady states of this. Here we have considered specifically for rho n equal to minus 0.98, which is a ring network. In this case, yeah, when in the absence of any processing delay delta equal to 0 in the K coupling strength versus delay space. So this black curve, right? So this is the region. This is the range where one can observe AD of this ring network. When as we increase the processing delay, you could see the spread, right? The range where the network suffers death state, quenched state, decreases, and above a critical value, this eventually disappears, thereby giving rise to the oscillation in the entire parameter space and rendering the network as an active network, so that we get back the robustness of the network, which again becomes active or dynamic network, thereby solving the purpose of the network for which it is being constructed. And here, this is the rho n the delta C has been plotted as a function of rho n, which basically range from -1 to 0. This covers the arbitrary network topologies. For specific rho n corresponds to a specific topology of a network. This results show that our results valid for any arbitrary network of any topologies. Yeah, and again, we have demonstrated this experimentally some time back. I stop here. Yeah, so thank you for your patience listening. Any questions?
Yeah, is there any questions from the audience? Let it be quick, because the students have to come back to the regular classes at 2:15. So one or two quick questions, please.
Sendil, this process of introducing delays in the coupling, processing delay, other delays, seems to be more complicated. Is there a way, other simple ways of introducing coupling such that the oscillations can be revived?
Yes. Yeah, you're right. So when you introduce delay into a dynamical system, this basically increases the dimensions of the system. It becomes infinite dimensional system as soon as we introduce delay into the system.
The coupling, introducing it in the coupling is the most difficult part, I think.
Yeah. So moreover, implementing it experimentally is also a very difficult thing, right? So in order to overcome this, so in this case, we have introduced this paper. In this work, we have introduced a limiting factor in the diffusive coupling. So by introducing this limiting factor, again, we could able to show that this can destabilize the stable steady state in all the known scenarios, and also in all the known phenomena, including the aging transition. We could able to show that this limiting factor could get back these oscillations. Which is published sometime back in Nature Communication. This work, yeah.
Okay.
So is there any other questions?
There was some chat or something. So can we generalize the chaotic and periodic oscillations under the Lyapunov exponent? Yes, Lyapunov exponent characterize even fixed points. Yes, one can characterize the dynamics, including chaotic, periodic, quasi-periodic, whatever be the oscillation using Lyapunov exponent.
Sir, this is Dinesh.
Yeah.
Sir, to attaining amplitude depth and oscillation depth oscillations, only delayed system?
No, right. So I have showed you the other system, the system with heterogeneities, right?
Oh.
Non-identical system where we have frequency mismatch, and also identical system with dynamic coupling, conjugate coupling, right? So there are other types of couplings which manifest this dead state, and there are also other couplings are there which are less studied, which are less interesting. But these are the predominant studies which have been widely reported.
Okay. Sir, but the low pass filters has inherently have a time delay.
Right.
So what about?
Yes.
So what about it coupling?
Yeah. Okay. So I'm also having those discussions here. So, but unfortunately, due to the time limitation, I couldn't able to discuss those things.
Okay.
Yeah. So in this work, right, through adaptive variables, which is basically the filterings over here, right? So we have shown that we could able to get back this oscillation by manipulating these filterings, right? Low pass filters in intrinsic variable and extrinsic variable. You could manipulate any type, engineer the dynamics that you like, either dead state or oscillating state. You could do it, and indeed, intrinsically they have delays. Yes, you are right.
Thank you, sir.
Right. Yeah, you're welcome.
So, is there any other question? So sorry, Sandil, we are running out of time.
That's fine. Yeah, it's fine.
The
It's
students
okay.
has to come back after 2:15. So I would like to wind up the session.
Right. If it would be offline, it would be more interesting, more interactive. Yeah. It would be more.
Yeah,
Yeah.
but
That's okay. Yeah.
Maybe
Be used nowadays.
I will invite you to
Fine,
offline.
fine.
Okay.
Right.
Maybe
Fine.
in February or March.
Yeah.
Yeah, it will be interesting. Yeah, because it seems that people have more questions.
Yeah. So more live interaction. Yeah, we could raise more questions and ask them move ahead by asking questions.
I strongly encourage the MSc students to write. If you have some doubts, please write to Professor Sendil Kumar and get clarified your doubts. So before winding up the session, I thank Dr. Sendil Kumar for giving a very interesting talk. He introduced the nonlinear dynamics in a very interesting way, starting from the simple linear circuits, and then he moved on to nonlinear circuits and so on. Even the MSc student can understand things now clearly. So he has, in fact, I observed that he has pointed out all minute details, which is not available in the textbooks. In that sense, MSc students are a bit lucky to know a few minute details. With these remarks, I thank once again, for agreeing to give a talk here, Sendil. Thank you very much.
Thank you, sir, and thank you all. Thank you for.
So with this, I wind up the session. Thank you.
Right. Thanks. Thank you all.
I will write to you, Sendil.
Thank you. Yes.
Other things.
Yes. Fine. Yeah. Right. Okay. Thank you.